Okay, um, in this video, I'll try to explain how you can derive the acoustic impedance of waves in solid media, which happens to be quite different from the air or fluid that we are used to. The radiation resistance of air or fluid mediums in acoustic transducers is quite well known for piston radiators having clamped edge conditions. It turns out that the radiation resistance in solids having Poisson's ratios less than zero point 0.5, the radiation resistance dependence on frequency as a function of frequency is quite different. So let's see. Here I have an axis symmetric model of a CMUT. It's a typical wafer bonded CMUT. You can see the dark regions. These are the meshed elements of silicon which are bonded on a glass, and you have a glass post, and that's the interface at which the silicon plate is bonded. And then you have the etched cavity, which is evacuated cavity. It doesn't have any air, it's vacuum, and silicon plate is suspended over it. By suspended, I mean it is free to move under the action of ambient medium loading, first of all, and then when the bias is applied between silicon plate and the bottom electrode, it establishes the electric field. So silicon plate is free to move, but it stays fixed. It is held fixed at the glass post, and the the displacement of it at the region where it is bonded is zero. But this does not mean that when the silicon plate is harmonically excited by a time varying signal, that it does not couple the energy. Well, the AC particle velocity is not zero. So that boundary condition does creates dispersive waves into the backing medium, which is a glass substrate in this case. So these meshed elements are that of glass backing. To the right, you see a lossy glass. So we have a so we have an interface of a lossy glass and a glass substrate, and the reason for this is to minimize any standing wave patterns at this interface, and because since we are interested in what kind of power flow we have, because of since the plate is vibrating on the application of applied time varying harmonic signal, and because of that it is expected to have normal tensile stresses and associated velocity fields, which are going to move the finite meshes of glass in both shear and longitudinal directions. So we're interested in how the wave propagates and how this power or energy is coupled by the vibrating membrane to the glass medium. So we don't want any standing wave patterns, and you can think of this as a perfect matching layer, which is going to absorb, or it is going to make sure that there is no reflection back into the glass substrate. Okay, yeah. So well, from FEMS or finite element analysis, if you can extract the tensile stresses, so this subscript n over here you see is the normal mode velocity and the tensile stresses. If you can extract this dxy, dxx, dxy from finite element analysis and the associated velocity fields using normal mode theory. Normal mode plate theory is that what it says is that you can decompose the plate vibrational modes, and or you can superimpose the orthogonal plate vibrational modes, and you can create the resultant velocity and tensile stress from that. Okay, where an is the amplitude of the respective tensile or the velocity field. Okay, so if you have this information, you can extract the power that is power per unit length in terms of velocity and tensile stresses that flows into the glass substrate or packing material of a transducer. In this case, it's a CMUT, which is built on a thin glass substrate. By thin, I means that the ultrasonic wavelength that is being considered is much larger than that of the physical thickness or the height of this glass substrate. So yeah, because if it is rigid or solid, then we have a very long backing, we have very thick backing, it is not going to move. But this is the case of a finite substrate thickness. The thickness is small, or you can say negligible, compared to the operating wavelength. Well, in this case, We have a the frequency you can see is about 77 kilohertz, and this is due to the geometrical parameter are as such that we have 1.4 mm radius plate and a 40 micron thick silicon plate, which is bonded to a 500 micrometer thick glass substrate. And if you consider the longitudinal speed of sound in glass, that is about 5,600 meters per second, and that gives the wavelength about 72 mm. So 72 mm, and if you compare 72 mm with a 0.5 mm glass, the thickness is negligible, nothing compared to uh, the wavelength, the ultrasonic wavelength, because of very high longitudinal speeds of sound in the glass medium. So it's a case of a thin backing. Okay. And if you have the tensile stresses and the associated velocity field, which are responsible for propagating those dispersive waves into the glass substrates, if you evaluate the power from finite element analysis, then it turns out that the power is an ever increasing function of frequency. Okay, you can see that yeah, the phase change is around 77 kilohertz, showing resonance at about 77 kilos. And the reactive power you can see on the other scale is negative. What it means is that negative reactive power it means that you have a capacitive loading, right? And owing to the structure of cement, it's a capacitive load, but that is expected. But the power, so when it starts vibrating, the power that it is coupling with frequency is increasing. Okay. So what I make out of this, is that if you think of it in a circuit convention, let me show you a circuit right away. So I think I have circuit over here somewhere. Yes. So you can see we in typical transducer equivalent circuits, you have an electrical section and a mechanical section. So the substrate loss is across the transduction force. So what it means is that if you have the power from FEMS in terms of which you have calculated in terms of the tensile stresses and the velocity of the waves, so this transduction force is what is responsible to propagate to make sure that propagation happens into the backing. Then the Z substrate, if you have the power and you know what is the transduction force, then Z substrate to be consistent with the circuit convention, if you have the power, then that can be expressed as the square of the transduction force divided by the power, right? Because the acoustic analogy of a voltage source on a mechanical section is the force, and force squared is just like volt squares. And if you have the power, then this is the acoustic impedance of the backing. Okay. So all you need to know is, well, if you have the power, now you have the power data from FEMS, all you need to do is to calculate what is the transduction force. And it turns out we have nice analytical formulations for those transduction force for the model. So let's see. Yeah. So let's recall the cross-sectional geometrical cross-section view of a single cement cell, and we have some geometrical parameters. So for example, Tm is the membrane thickness over here, is the radius. The profile radial parameter is R. X of R is the silicon profile, which has been depressed by the application of both the ambient loading and the electrical port. F consists of both the electrical part and the mechanical ambient loading, right? Yeah. So in order to calculate the capacitance, because of the profile, you see it's not a parallel plate capacitor. Okay, that there's a bottom electrode and the top electrode is silicon itself, which conducts when it is biased at a certain static. So what happens is, owing to the establishment of electric field, thereby since it cannot move at the post where it is bonded, it does create a static profile like this. Okay, which is non-linear. The profile is non-linear. It's not a parallel plate capacitor. So you cannot think of the capacitance simply in terms of the circular area like pi square over the etched cavity gap height. You have to calculate the capacitance in terms of the profile of the membrane profile. Okay, So how to do that? Well, there are texts available on calculation of such thin plates profile having aspect ratio around 80. That is, the aspect ratio means if the ratio of A by Tm is about 80 and the plate is being depressed by uniform force, and that depression is not much so that the membrane is out of elastic regime, or there's a geometric nonlinearity in the material or plate itself, then um, you can express the radial profile of a thin membrane depressed by uniform pressure as such. Okay, this is an analytical formulation for thin plates which are being depressed by uniform pressure, and R is the radial variable. So where do we need this profile? Well, we need this profile to calculate the incremental capacitance. So if you consider a infinitesimally width small element of the membrane having width dr and having radius r, then you can see the numerator is an area, and then the profile is as such that you have to subtract from the electrical length of the cavity. It's not the physical, it's the electrical length. I mean, the electrical length is, if you consider two capacitances, you have a passivized film and underneath silicon having thickness of Ti, and a series combination of capacitance because of this passivation and the evacuated cavity Tg. The parallel combination of that capacitor is Tge, that is Tg plus Ti epsilon naught. So materials like hafnium oxide or aluminum oxide, and for very thin, like those passive films which have been deposited by, let's say, ALD processes, in terms of having very thin nanometers thickness films, then the effective gap height is also, you can say that it's Tg, because permittivity for materials like aluminum oxide is 10, hafnium oxide goes to 20, and it is in nanometers, could be very small. Second term could be a very small quantity. Okay, yeah. But anyways, if materials like silicon dioxide having larger permittivity like 3.9 or 4, then well, you have to add this to Tg. Okay, and in the denominator you have to subtract the profile, so you have the capacitance function like that. So this is the incremental capacitance, and if you want to find the total capacitance, this expression has to be integrated with respect to dr, okay, and the width of that element, and that width of the element goes to the total is the radius a. So from 0 to a, if you integrate this, you have the total capacitance. And this comes out in form of transcendental functions, which are trigonometric hyperbolic functions. And a plot of such function is shown over here. So what it says is that as you go on increasing the bias when the plate is moving, it's not like that you have a capacitance equal to T naught, which is very close to what you have. You will have if you have a parallel plate circular capacitor. The expression is very similar to a capacitance that one can understand, but owing to the profile, the nonlinear profile, this grows. Okay, so it could be like 1.2 times before it collapses, and this curve is well, there is a family of curves. Just a single curve is shown over here, just to illustrate how the transcendental function looks like. Because this means that the device is in vacuum. So the only force that is depressing and making the profile as such is the electrical force. You don't have ambient force. Okay, but if let's say the Fg is like 0.9, okay, that means um, the ambient force is like 90% of the force required to collapse the membrane. That in that case, the curve can start from like 2 or 2.2 or something. Okay, and it might grow more than 2.4, 2.5. Okay, yeah. So that happens if you have a very thin plate and you etch very not deep but shallow cavities. Yeah, so in that case you will have a large ambient force, that is not large ambient but large ambient normalized force. So that means the plate is already very close to the substrate. Okay, but yeah, I mean, I might have to more time in explaining the capacitance, but the importance of the capacitance comes when you evaluate the transduction force. So we need this capacitance in our model, analytical circuit model. So this C naught is what you have over here, but it has to be multiplied by the by the transcendental function G over here. So it's not C naught, it's C. So it has to multiply with the G function, considering the profile of the plate, which has been depressed by the force, electrical and ambient. And because of that profile, you have more capacitance as compared to the parallel plate capacitor. Okay. Yeah, because the gap decreases at the center. Okay, so you have a nonlinear profile, the capacitance is more. So this goes into the model with the parasitic capacitance, which means that you will have some capacitance of wires or channels, and then when you apply a harmonic time varying signal at the electrical side, there will be a change in the capacitance because of a vibrating plate, and due to the change in capacitance, you will have a alternating current, an AC capacitive current IC on the electrical side, as well as the particle velocity is changing. So this is modeling the particle velocity of the membrane. So how you evaluate the transduction force, which is the mechanical section part of the circuit? Well, you consider the for a harmonically excited membrane, which is responsible to create, which is not only making the membrane vibrate and radiate ultrasound into the front fluid medium, but it turns out that it also couples some energy back to the substrate, which is bonded to the silicon plate, and this coupling happens in forms of dispersive waves that I have talked before, and you can calculate the power in terms of the tensile stresses and the associated velocity fields if you invoke the normal mode theory. So if this is the power, then the transduction force, the instantaneous transduction force, can be evaluated by taking the partial derivative with respect to the profile of the instantaneous energy in the cavity. The energy is half CV square, and this C is where it comes for the profile. So this is, you have the transduction function, and you have C naught, so this is half CV square. And if you take the derivative, then this is the form of the transduction force. So you have derivatives of the transcendental functions in terms of time varying profile of CMUT. So for the same geometrical parameter, you can see the maximum energy that it couples to the ultrasound or radiation medium is around 77 kilohertz. And if you take the ratio of this FR square to the power, real and imaginary parts, then you have the radiation resistance, I say. And the radiation resistance is that, well, it sort of shows that the resistance is more, you can interpret this as there is more leakage at low frequencies as compared to the higher frequencies. So what it means is that at DC or at low frequencies, you have elevated trends. You will see elevated real part of the measured impedance of CMOS cell. There are going to be the baselines. The baselines are because of this radiation resistance. And the other part, which is the imaginary part, because the reactive power is as such, showing the capacitive load, it turns out that it's the compliance or the capacitance of the backing. So you can think of thin substrate as a CMUT built on a thin substrate as a bilateral CMUT. That is, it's not only the silicon that is moving, but there is a substrate which is not very easily moved, but because it's a solid and it's not flexural like silicon. So it does have a compliance capacitance, just like silicon over here in the front plate. And you can see in the model, the CRM and LRM is the compliance capacitance and the mass of the plate. So as long as the compliance is linear, by linear compliance I mean that there's no geometric nonlinearity, there is no material fatigue, there is no, the swings are not large. So that means that it obeys Hooke's law. Okay, so the displacement of the spring is in proportion to the force, as long as the geometric linearity conditions are maintained. Yeah, but it's difficult to move the glass, so the compliance is very low as compared to what you have with silicon front plate. Yeah, so it's going to be a smaller capacitance. Yeah, so that capacitance shows up over here for the glass. So it's a I can say a CMUT having two plates. One is the silicon plate and the other is the glass substrate. So, the radiation impedance are very different. So one is the solid medium and the other is the fluid medium, right? To which it is radiating. So it is radiating into the two mediums, two acoustic mediums, very different mediums, but because the materials are different, one is the fluid, uh, having Poisson ratio close to 0.5, just like soft polymers, RTV rubbers, and the other is the glass, having Poisson ratio 0.2. So the radiation resistance is like this for glass medium, which is very thin. And when you measure the impedance of such thin substrate cells, you see in the measured real part of the impedance data that you have dropping characteristics, or the real part of impedance decreases with frequency. Okay. Yeah, while the susceptance or the measured reactance is growing with frequency, and that is typical of CMOS, which shows a capacitive load. Yeah, so this is also reported in in CMOS-based lamp wave devices, because CMOS couple elastic waves into the substrate, and they have, if you go into this text, I think I've already talked about this in my previous videos. Yeah, if you just go and have a look on this reference, you will see that they have derived very similar radiation resistances. This is the resistance, the real part of the substrate, and they have a very thin backings, which for which they have characterized through laser vibrometer analysis that they have both the symmetrical lower order symmetrical anti-symmetrical lamp wave modes A naught and S naught, and well, A naught vanishes for very thin membranes with thin substrates, but S naught is it retains a very stable or steady state values if you remember the dispersive curves of lamp waves, but the higher order modes are in cutoff. So they talk of lamp waves, and they exploit this um, power that the harmonically excited membrane couples to the medium in form of lamp waves, so it becomes a lamp wave device. But the radiation resistance that these waves suffer is very similar to what we have for thin substrates, if you think of it in terms of elastic waves. So the substrate thickness is for given a substrate thickness which is thin compared to the operating wavelength, which is the case over here as well. I think these were built for 2.1 megahertz, and if you compare the product of the operating frequency and the thickness, and you look at the dispersive curves of lamp waves, then you have A naught and S naught modes as well, which are excited for such operating point of CMOT. But the radiation resistance is very similar to what we can derive from the power that is being coupled to the backing, and this is also experienced or has been observed in the measured impedance data. If you want, just I'll just briefly show you. So yeah, I have some cells over here, and but this is conductance. This is not. This is conductance. You can see, and this is not resistance. So if you plot the data is taken as such, but if you plot it in ohms, then it's the other way around. The baseline starts at the elevated level, which is higher, and then at high frequency this goes down. So these baselines are what I'm talking about. These baselines are created because of the power as such, okay, or the radiation resistance, which is inversely proportional to the frequency, okay. But if you yeah, maybe I can show you with the ohms. Yeah, over here I have data with ohms, and this is what I'm talking about, okay. So this sort of trend is what creates these elevated baselines, okay. If you don't have this loss with the transduction force, so this is a linear model. The transduction force is linearized in terms of electromechanical coupling, turns ratio, and the spring softening capacitance. If you don't have this loss, the shunt loss with transduction force, like over here, we have open circuit conditions for, say, rigid banking or a solid banking, then you don't have the baseline. It's not just the baseline, but I would say the loss is notorious enough to reduce the measured quality factor. You see the quality factor is very different in these two models. And what the measurement suggests is that, yeah, you have those kind of baselines And I think I've talked more about this in my previous video, so I'm not going to waste any more time. Uh, you can go and have a look on the previous videos, but this kind of trend has been reported in the CMUT literature, which for CMUTs having thin substrate, for example, this was presented in 2004 IUS conference, and they also observed a similar trend for very high frequency linear CMUT arrays that were built for high resolution intravascular imaging. And they reported a similar trend of baselines, and these baselines were suggestive of the loss to the packing in form of dispersive elastic waves. Okay. Okay. So thank you for hearing, and have a good day.